All right. Before we get started with that, though, let's take a look at this surface. Use a computer algebraic system to find the volume that it encloses. So we need to find a volume, and it looks like we have to find the volume of this solid. So if we imagine that this whole thing is a solid, and we can set up our inequalities like this, and this time our rho is kind of controlled by this function. So if we start from the origin at 0 and then it goes out to every place on that surface, and then we would have this. And then we might as well use the actual, I still had this highlighted when I copied it, so m is equal to 6, and then n is equal to 5. And then our phi looks like it's the whole, it covers the whole thing, so the phi probably goes all the way down, and then theta goes all the way around. So if we had stopped halfway, like at the xy plane, then our phi would go from 0 to pi over 2, but this thing goes all the way down, and then we let our theta spin all the way around. So that would be it, really, in terms of setting things up. Our dv, remember, is the rho squared sine phi. So this one, it's imperative that you have to integrate with respect to rho first, because you have limits for rho that's a function of phi and theta. So we'll write that down. And then we have constants for the rest. So we can, what was I going to say? Oh, take out our Mathematica and then do our integral. So 0 to pi, zero to pi, and 0 to that function 1 plus 1/5 sine 6 theta times sine 5 phi. Our integrand is just a Jacobian. That's rho rho squared sine phi d rho d phi d theta. Okay, so we wait and wait and wait. Oh, 136 pi over 99. That's nice. It is actually doable, right? It'll just be rho cubed over 3, and then it goes from 0 to the top limit, and then you take this thing and then you cube it. I mean, it's not impossible to do by hand is what I'm saying. Yeah?
If you were to stick that into the same online limit,
Well, I think what Emma was saying, and it worked? Oh, okay.
But it was giving me a decimal. I put in the decimal.
Okay, good. Yeah, it might time out depending on your connection or depending on how busy Wolfram is. I mean, I think maybe if you do it like at 3 in the morning, because that's also how Siri, you know, when you do Siri, and then you say, "Hey Siri, what's this?" And then I don't know if you noticed, but if you look at the results that Siri has, it goes back to Wolfram Alpha. You know that? Probably. Hey Siri. Siri's not available. I don't have a connection in here. Oh, maybe if I could just mess around here since we're just reviewing anyways, right? Just kill time. Hey Siri. Integrate sine squared theta. I'm not sure I understand. You guys can mess around with it. But like if you ask for like you know, currency exchange and stuff, it turns out that Wolfram Alpha is now like an interactive data bank for a lot of different things, not just math. And so you can see stocks and currency and population and stuff like that. So I wanted to copy this. Can you put, do you remember what decimal you put in? No. I'm going to say if you can compare it to this and see if it's the same answer. 136 pi over 99. It seems right. 36 pi over 99. So since we have this surface here, this looks like a cool surface to look at. Let's see. This thing doesn't have rho. I don't think it does it? No. So I think it sticks with R, but if you use phi and theta, it's going to understand that it's in spherical coordinates. 1 plus 1/5 sine 6 theta sine 5 phi. What's cool about this is that these numbers are like different parameters. So if you change it, it'll change to whatever. So let's change this into, well, let's make it a slider 3 to 10. Ready? Wait, stop spinning. Wow. And let's change this into B. Wow. Cool. So anyways, with the combinations of A's and B's, you can design any tumor you want. Well, you know. One of these days, you're going to be working in a lab, and there's going to be some biology person saying, hey, can you make the shape of this tumor? And then you got to think, oh, I remember this in Calc 3. Wait, it's rho equals 1 plus 1/5 sine 6 theta sine 5 phi. Is that it? Yep. There you go. You'll be a superstar. All right. Anything else? Oh, there's one other cool thing that I wanted to talk about. Since I have Mathematica up and everything, this is just for fun now, since we're all just having fun. We having fun yet? Kind of fun. Now, in Calc 2, maybe a professor might have given this to you as a problem before you even learn how to integrate. And of course, when you look at this and say, oh, I would need trig substitution or something to integrate this. And so they would have given you this. I sometimes give this problem to my Calc 1 students at the end of the semester. What's this equal to? Give up. How? What?
Because that results in an infinite series via the inverse product rule.
You could.
And which ends up being the arc sine function.
Maybe. There's an arc sine there. Yeah. It's top half of the circle. Multiply it times 2. It's a whole circle. Radius 1, area of the circle, radius 1. So without doing any calculus, this can be done, right? I guess if we put r here, then we get pi r squared. Okay, so this is essentially just area of the circle. Now, if we take this up a notch, up a notch, oh yeah. And then I can say this is, let's call it D for this. Well, this will end up being, what is this? What is it? Which is volume. This is volume of the sphere. Right? So now, if we follow this progression, if we call this E, and take the triple integral I should have just put dz or dv here. But if we do this, this is, what do you think this is going to be? Not what this is equal to, because I don't know. I'd be impressed if somebody can actually tell me what this is. I don't think I know the formula off the top of my head, but this would be kind of like the volume or the hypervolume. Which is something that we've kind of mentioned, but we said, we're not going to talk about hypervolumes because whenever we do triple integrals, we'll just say, oh, it's like finding the mass or finding the center of mass and inertia and stuff like that. We kind of stuck with those applications. But geometrically, we can think about this as just another extension, generalization of finding the area of a circle or a volume of a sphere. Now we take a look at a hypervolume, you know, the fourth dimensional volume of a four-dimensional sphere. And E is going to be the shadow, which is 3 dimensions, a 3-dimensional shadow of a 4-dimensional sphere, whatever shadow means. So we know the formulas for the area and the volume, but it would be nice to find this formula. And the way to do that is to actually do this integral. So let's begin to compute this integral. Now, I'd like to compute this integral, but my E is a sphere. So it would kind of be natural to what? Go into spherical coordinates. So we can go into spherical coordinates, and then let's see if we can compute this integral. So in spherical coordinates, your E is going to have a radius that goes from 0 to whatever the radius of that sphere is, the solid sphere. And then our phi goes all the way down to pi, and then our theta goes all the way around 2 pi. And remember that x squared plus y squared plus z squared is equal to rho squared in our transformation. And so now we can rewrite this integral to look like 0 to r, 0 to pi, 0 to 2 pi. I don't usually write it like this. I usually write it inward out. But we have r squared. R is a constant. X squared plus y squared plus z squared is rho squared. And so the dv becomes a rho squared sine phi, d rho, d phi, d theta. Now this is doable. The difficult part is the Rho integral. You can integrate sine phi easily, and there's no thetas in there, so you can imagine a 2 pi sitting out there already. So the difficult part here is this, which would require trigonometric substitution because you have an r squared minus rho squared under a square root. So because of that, I'm not going to do it. I'm just going to have Mathematica do it for me. So I'll just copy and paste this business since we just did it. And I'll just change things. So we have constants is r. I think that's okay. And then I just tack in the beginning here. Okay, I think that's it, right? Oh, there's a 2 out in front, so let's put that 2 out in front so we'll get it all cleaned up. And then we'll run it. Run it. Oh, shift. So when we run it, we'll get a formula for the hypervolume of a 4-dimensional sphere of radius r. Negative. Why don't we just pretend it said positive? The other thing that people do is sometimes because of symmetry, and there's symmetry all around, they cut this down into, instead of going from 0 to pi, they go from 0 to pi over 2. And then let's see if we can cheat a little bit and go to pi over 2. So multiply this by another 2. And then instead of going all around from 0 to 2 pi, we can go from 0 to pi. That cuts it in half. And then another pi. It's another. So what if I cheat and just multiply this times 4 and then have this go from 0 to pi over 2 also? Because usually when signs start doing all those weird trig things, they start giving you different values. Let's see if this comes out positive. No. Damn it. 0 to r. Is it this answer though, except positive?
Yeah.
Okay, it's positive. I'll have to think about why it's negative. Yeah.
When you integrate with respect to p, then you change the order. When you integrate with respect to p, then make it first.
But would that make a difference? Sine going from 0 to pi, it goes from 0 to 1, so that just contributes 1.
Well, it would make sense to make it I just don't know why I cannot make it with respect to all that.
I'm a little worried about r, and let me see if I can just change this into a different constant. No, it still shouldn't be. Yeah, it's still negative. All right, well, make it positive, and then we're all good. Anyways, you can create formulas for, now this is a formula for the hypervolume of a four-dimensional sphere, and you can also begin to extend that to finding volumes or hypervolumes of five-dimensional spheres and six-dimensional spheres. And if you can see the pattern here, how it goes from one level to the next dimension, then you should be able to set up the other integrals. I think that's kind of cool. It's one of those projects that I worked on one weekend or something. I don't know. The other thing is that sometimes after we do stuff in class, I try to take a look at how it would look like in pictures in case I was able to get the picture done. And so, the quiz, yeah. The quiz that we took yesterday, I was able to come up with pictures of those fruits using the graphing calculator. Where did I put it? Put it here, and I forgot to. So I used graphing calculator to create this. And next chapter, you guys you'll start doing these things where you need to parameterize. You know how you parameterize curves. Next thing we're going to do is called parameterizing surfaces. And when you parameterize surfaces, what you're going to do is it's like a three-dimensional object that has two parameters. Usually in the book they use S and T. But in a lot of programs, they use U and V. And so here, I was parameterizing these things. And so one side of that orange slice would be one of these graphs. And then I enclosed it with another graph. That would be like the other side of the orange. And then the peel part of the orange is this parameterization. And so what you're going to do is we're going to take those the cylindrical and spherical coordinates that we've been talking about, and we're going to work on parameterizing surfaces using those and other things as well. So like the peel part of the orange here gives since that's the one that's part of the sphere, that one has like a spherical parameterization where you have rho and then sine of phi and then cosine of theta, and then rho sine phi sine theta, and then rho cosine phi. And so those are some of the things that you're going to, something to look forward to. And here's the cantaloupe, bottom part of the cantaloupe. So the tricky part, I guess there's not that tricky. You're just, your phi goes from pi over 2 to pi, since it goes from the axis down below. Where's the pineapple? Or here's the watermelon. So the pineapple, I wrote the function on the board. It turns out that I went a little too low with that function. I needed to go higher. So that function, instead of x squared plus y, or x plus y plus z is equal to 5, it should have been higher than that, like 6 or anything higher would have done. If I had 5 in here, it actually would have gone below the x-axis, and so that didn't quite work out so well. So I'll make adjustments when I grade your quizzes. But here, this one has the cylinder on the outside, the cylinder on the inside, the annulus in the bottom, and then this slanted annulus here, which is the red thing that you're seeing. And those things are described, almost all the things here is described in cylindrical coordinates. And then what was the fifth one? The fifth one was that the watermelon, taking the top and the bottom part out. So we have phi going from pi over 4 to 3 pi over 4, right? Doesn't go all the way down. This one was an easy one. Turned out to be pretty easy. That's just a pineapple slice. It's just a cylinder, a quarter of a cylinder. The only thing is that z went from -2 to 2. I mean, which isn't that big of a deal. And the last one I didn't do because can't. It would have been too difficult to do. So I gave you kind of a bogus question because I was running out of ideas. So each of those problems would be worth 2 points, and you have 6 problems total. So you have possibility of getting 12 out of 10 points for your quiz. No, the quiz that you guys did yesterday. What? I know, the 7th problem I didn't do it. I'm not going to count it. All right. So I can post this up. I don't know if it'll be helpful. Do you guys feel okay about the quiz? You guys think you nailed it? Or did it seem difficult? So I'll post this anyways. I made the solutions. I took a couple of snapshots from different angles of those figures that I just drew, and then put the solutions on the right side. I hope it's correct. Does that look all look familiar? You got rho. So this is the 10 segments. I'm only taking a look at one segment. So the whole thing is 2 pi. You divide that by 10, and then you get one of those segments. So that's the theta. The cantaloupe is in the bottom. So the phi goes from pi over 2 to pi. This is fairly easy, right? Just goes down at a 45-degree angle from the positive z-axis. This one, since in the board I wrote 5, it actually should be 6, but I'll grade it according to that. So the equation was given as x plus y plus z is equal to 6. So if you solve for z, this is what you get. But when you change it into cylindrical coordinates, you don't have x, y's, and z's anymore, right? And so that actually needs to change into x is equal to r cosine theta and x equal to r sine theta. But I'll be flexible. If you kept the x and y, and maybe you'll get 1 out of 2 points, or I'll just take half a point off, depending on how many glasses of scotch I drank already. The watermelon. It's, the phi goes from pi over 4 to 3 pi over 4, and then this last one is pretty straightforward. Okay. Would that be interesting, or should I not bother posting it? Not post it. Okay. All right. Information for the exam is up here, and I don't know if you guys downloaded the review. But we are looking at 5 problems on this exam. Okay. So the first problem will be on directional derivatives and gradients. So directional derivatives, remember there's certain rules in the gradients, there's certain properties that you should know about that. So you need to be able to find basic directional derivatives. You need to be able to find equations of tangent planes. Those are gradient properties. You need to be able to find normal vectors, things like that. Problem number 2 will be an optimization. So finding critical points is going to be important. You should know the second derivative test. I think I'm not going to put an extreme value problem business there, where you have to find the critical points and then find the things on the edges, on the boundaries. But there probably will be a Lagrange multiplier problem in the optimization. So you should have practice doing some Lagrange multipliers in 2 variables. So I won't go to 3 variables. The third problem will be on double integrals. So setting up double integrals, changing it to polar, switching order of integration, and these or finding mass and whatever the other physics stuffs, other applications. But in this case, I'm only going to ask you to set things up. I'm not going to ask you to compute the integral. Okay. So I noticed on the quiz where I asked you to set up some integrals. Some people actually worked out the integrals. You can do that if you want to waste your time during the test, but I would suggest that you go through and finish the rest of the test before having fun trying to solve the integral. I'm not going to expect you to find these integrals. I just want you to set them up. The last one would be triple integrals. That would, of course, be going into the cylindrical and spherical coordinates. Okay, I will not have a strange change of variable problem from 1510, like that last homework. So I won't give you another change of variables. The only change of variables you'll be doing would be polar, cylindrical, or spherical, which you already know the Jacobian for. Okay, if you don't have it memorized, it should be in your sheet of notes. The last one is short answer concept questions. Just a bunch of random things from the 2 chapters. Chapter 14 and 15. What?
What is Find out.
No. What is math? Yeah.
So this is replacing the true false.
This is replacing the true-false from your review. So in your review, you had a true-false set of questions. Now you have the short answers. So if you think about the first exam, in the review, I had short answers, and then in the test, I gave you a true-false. So imagine that little switch thing. That's kind of like what you... at the end of each chapter, Chapter 14 and Chapter 15, there's concept, something, and then there's true-false questions. You can look through that to see if you can answer those concepts, and then those are the kinds of things that I would be looking to put here. The review has true-false questions, but the test will have short answer questions. I think they kind of go hand in hand. They're concept checking ideas. I was looking for the review and I couldn't the solutions, and I couldn't find it. I don't know if I want to make it up from scratch again, but I'll try to look for it again. And the solutions to the review coming soon. I hope they come before your test. Soon is relative.
So I noticed that, it's completely out of the page, sorry, but I noticed that the determinant for 3x3 matrix that you were taking the Gaussian over with a three variable set is it's basically if you were to treat XYZ as for XYZ gradient that there is as, and then take the scalar triple.
Yeah. So if you're comfortable doing the scalar triple product, that's essentially the determinant. You have those three numbers, or you have those three vectors, and then you do whatever you do to find it. That's it. Okay. So here's some true-false questions to study. They kind of lend towards the concept questions. And this is an exam that I gave maybe last semester or 2 semesters ago or something. So here, I try to put the idea of directional derivatives and gradients in the context of an application or something like that. So in this case, you have an ant crawling on a surface, and then if the ant moves according to a map from one point to another point, what's the ant's rate of change in height? If you spear the ant perpendicularly, then what's that line if it's a normal spearing? And then as opposed to a sideways spearing, you want to take it directly from the top. And then after you spear the ant, it starts oozing its guts. And so if the guts are going to ooze down in the fastest direction, what direction is it going to ooze down? And then you decide to squash the ant with a tangent plane. Find the equation of that tangent plane that you used. And then so it's not oozing down the surface. It's actually, if it oozes down the tangent plane, now what is the vector that's going to move on a tangent plane? And so that one's tricky because it actually is asking for a tangent vector. Because it's on the plane, it's tangent to the surface. And so you're actually looking for a tangent vector. But you're not looking for the tangent vector in the x or y direction. You're looking for the tangent vector in some other direction. So that one's a little trickier.
Do you have an ant problem or something?
No, I was just, I had a friend who was a math teacher at UC Santa Cruz, and, I go to his house, and then he's studying ants. He studies a lot of things. So anyways, he showed me, he had two plants and they were kind of connected by the leaves, and then he took some water and he poured it into this one plant, and the ants were in there, they're in the soil, and so they all crawled out and moved to the other plant. You can see this marching ants, and he was saying if you just keep them all contained, they're not, you don't leave any food out, it's not going to go all over the place. You're going to keep, as long as you keep contained, they're really fun to study. So I don't have a problem with ants. They're just, fun to spear and squash. And optimization type of problems would be finding critical points and classifying them. I know on the quiz I asked you to do this, and I know on the quiz you didn't have a sheet of notes readily available, although a lot of you guys were able to get it. But now you can just write down your second derivative test and make sure you know how to do it. Also, write down a couple of examples on how to find critical points. We didn't really talk deeply into a lot of the little intricacies for finding critical points. So make sure you're comfortable being able to find critical points of functions. And once you do that, you plug it into the discriminant. Plug it into the discriminant, and then you figure out your signs, whether positive and negative. Here's a simple Lagrange multiplier problem. So look for other Lagrange multiplier problems that you guys might have had in your homework, and get kind of comfortable with solving for the x's and y's and stuff. The double integrals. So you can, like I said, you can see some problems. You might see some problems on like a mass or I didn't think about putting a probability question in there. So the only physics type of thing that you might see, if you see physics type of thing, would be mass. And then switching the order and then changing into polar coordinates would be another good thing to know. Question?
Yes. Can you do an example where we have to draw reviewing examples, something like that?
Like number A, 4A? All right. All right, so let's do this problem. We have y limits. So the first thing that I would do is to try to find out how things work out in y. And so I have y limits, and my lower limit, and it's important to go low to high, left to right. Lower limit is x squared. So I have y is equal to x squared as my lower limit. And thinking ahead, this is a y vertical line. I'm looking at this is the lower limit going vertically, and the upper limit is 4. So I'm going to the parabola to 4. And then my x goes from 0 to 2. Now, if I take, there's 4 things here, there's 4 equations here that I'm looking at. And I'm looking at 2 equations, and I'm marking it with my constant limits. So if I were to look at this, I would look at the x squared function. Y is equal to x squared, and then y is equal to 4 is a horizontal line. I would imagine my when you check where your line goes in and out, I would draw it vertically, and this is what I'm seeing. And then my limits, constant limits, go from 0 to 2, and I'm assuming, if this is written correctly, that the x value for this intersection is going to be 2. So I can clearly see now my region, right? So that's my region, but now I want to switch the order of integration. So instead of going y first, I want to go x first. And that means if I want to go x first, I have my region all set up over here. I want to draw a line parallel to my x-axis and see where I enter and exit my function. So I enter my function here from 0, x is equal to 0, and then I have this function that I need to find x by itself so that I can write it as a function of y. And this will give me the square root of y. And when you take the square root, remember there's a positive, negative part, and so you can convince yourself that this is the positive part. The negative part's over here that you don't need to worry about. So this would just be the square root of y. So that would be my upper limits, and this would complete my inside limits. Now the outer limits are constant, so I just need to look for constant in the y, and that would go from 0 to 4. So now when you rewrite it, make sure you write it as dx dy instead of dy dx as it was originally written. And x goes from 0 to root y, and y goes from 0 to 4. Okay? All right. Yeah. Why would we need to do this? Because this integrand might not be easy to integrate with respect to y in the beginning. And so if you change the variable, you might have a chance of being able to integrate it. If this was, for example, e to the y squared, you can't integrate this with respect to y. But if you switch it, you integrate with respect to x first, you might come up with an extra x there. Maybe. That's the idea behind switching. Any other questions? All right, so in the review, the last problem is the triple integrals, but on the test, it's actually the fourth problem because I switched the order instead of having the multiple choice business. Instead of having it first, I have it last, so this is your triple integral type of problem where you should be able to do something in cylindrical and spherical and Cartesian coordinates. So you should be able to write these things in these different coordinate systems. And so especially when one of them is a 0, beware of trying to figure out, is that the bottom half, is that the right half, is that the front half? So there's possible things that could happen. All right? You guys okay for this test? All right. I have a little review wrap-up thing that where is it? Oh, probably should